Another very cool company that's becoming a very big brand very quickly is a company called Docker. How many people have heard of Docker? A lot of people. That's no surprise. So let's play a quick video for the rest of you that don't know Docker. We'll give you a little insight.
We feel that the time has come really to change the way that people think about how you create, develop, ship apps. I'm Ben Golub. I'm CEO of Docker. As a project, we have over 400 contributors, even though there are only 35 people in the office here. We've been downloaded close to 3 million times. We are deployed in lots of different use cases, from places like eBay and Gilt and Groupon, to lots of banks, lots of healthcare organizations. We've established great partnerships with folks like Rackspace. We think what needs to change is the notion that in order to make something portable, you need to take the application, which may be measured in megabytes, combine it with an operating system that's probably measured in gigabytes, emulate a whole server and move that whole unit around. But in fact, there's a much simpler model, which is to simply containerize the application. We took a lot of the underlying technology around containers and said, if we made these really easy to use, portable between environments, accessible to the average developer or the average sysadmin, and built up a library for people to collaborate, the world could change. Basically, with the container model, you just take the application itself and its dependencies, and you run it in an isolated way on the host OS. We think it should be easier to ship applications from one data center to another than it is to ship car parts halfway around the world, but that isn't the case today. But with Docker and standardized containers and the kind of work we're doing with people like Rackspace, we're making that a reality. Collaborative approaches towards building, shipping, and running applications is really the way of the future.
So solving with containers, I think that's a kind of a new theme. We're hearing a lot of customers starting to dig into how they can solve some of their challenges with containers. We're very excited to have Docker here today. We have Ken Cochran, who's an engineering manager at Docker. He actually writes code at Docker, and he's going to help us understand what the future looks like in terms of applications. So Ken Cochran, please welcome Ken.
Thank you, John. So I think he asked this before, but I'm going to ask it again. How many people have heard of Docker before? That's pretty good. How many are actually using it today? All right, so a lot less hands. It's kind of interesting. When I started talking about Docker, the first couple presentations, I'd mention that, and no one would raise their hand. Maybe one person in the back of the room. So we've come a long way in a short amount of time. I've been with Docker for 2.5 years, so I've seen it grow from an idea to what you see today. But a lot of that would have been possible if it wasn't for companies like Rackspace, who help feed the open source community and help contribute to the community around Docker to build what we have today. So what I'm going to talk to you today about is the future of applications. I'm going to go over a little bit of agenda here. The matrix from hell is kind of a popular thing that we like to talk about. We'll go over what Docker is, what the containers are, and kind of what we see as our future, the future for applications. But before I talk about the future, I need to talk about the past, and then we'll kind of move towards the present so we can kind of see where we are today. I've been developing software for about 15 years. When I first got out of college, I worked at a large company developing enterprise Java applications. And these applications are very big, monolithic applications. And the development cycle was pretty long. It would take maybe months or quarters before you finally delivered something. And when you did, you usually deployed it to a single server. And this worked well for a while, but as the internet got more popular and more people were using websites to do more things, what happened was you needed to scale that application. You needed to handle more traffic. So some of the things that we did to start off with is we would maybe move static media out of the application and maybe serve it by Nginx or Apache, something that's dedicated to serving static media. The next thing that you might have done is you might have added a second server and used a load balancer to scale the load between the two. Going a little further, you might have added a web cache or a data cache between your database and your application. A little further, you might have broken out your long-running transactions from doing request response into the background. So you have workers, and those workers need a queue. And so as you can see, as we kind of expanded, as we got older and closer to what we have today, we have a completely different environment. The environment is a lot more complex. There's a lot more moving parts. and we do development in a lot more iterative fashion. So instead of doing something that's going to take a month or a quarter before we deliver, we're doing them in weeks, days, and maybe even hours between releases. So these new development stacks are basically built with small, loosely coupled components. And these loosely coupled components are not served on just one server. They're served over many servers so that we can handle scale. So if you have an issue with your background workers, you can run those on many servers, and you don't have to worry about scaling up your database. So what we have today is basically a bunch of different components. You have your static website, your user database, your web front end, your queue, your API endpoints, your workers, and all of this stuff needs to get deployed. You might deploy that on your development environment. You might deploy it on your test environment. Either way, you have to take care of it. This complex development environment is getting pretty complex. If you want to see how complex someone's development environment is, you can ask them one question. Just go up to your developers and say, how much time would it take to onboard a new developer today? Basically, if you had a new developer start today and you give them a new laptop, how long would it take for them to sit there before you would actually have the ability to start contributing code? You'd be surprised at some of the answers you'd get. If you polled the room today, you would have answers as little as a couple hours to as much as a couple days. That's a lot of time that's wasted trying to get someone's machine set up, all because of this new complexity. This new complexity that we're talking about, we have a cool name for it. We call it the matrix from hell. Basically, the columns describe the different environments that you're going to have, and the rows are the different components. And there's some services and tools out there that can help you manage this. But what ends up happening is that's just another item that you end up adding to the matrix that you have to manage. So it just gets a little complicated. And what we're trying to do is think of a way to simplify that. One of the ways that we did was we sat down and we said, let's look through history to see if there's any other industries out there that are very similar to what we're trying to do and see what they did. We ended up finding one. It was in the cargo industry. So before 1960, if you wanted to ship something, what ended up happening was you had to figure out who was going to ship your stuff from one place to the other. And this shipping company needed to manage all the different products. Whether you're shipping car parts, you're shipping coffee, bananas, whatever it may be. And this was a really slow and expensive process because the people who are shipping everything need to have a different process for unloading different types of cargo. If you're unloading bananas, that's a totally different way of unloading bananas out of a ship than it is compared to unloading a car. So you had all this manual process, it was slow, it was bulky, and you had a lot of issues when someone's banana load gets squished next to a bunch of anvils and they show up and they're not full bananas anymore. They might still be bananas, but they're a little smaller and squished. So what they did is they came up with this idea, is they said, hey, let's create this box. But not just any box, it's a standard intermodal shipping container. This box has a standard height, width, length. And what it does is it allows you to make it easier to basically put all your hooks and your holes in the same place so that when you're doing anything, it's a standard. It doesn't matter if you're shipping bananas, you're shipping car parts, it's the same box. So anyone that's moved knows how complicated it is to put all the stuff that you have in your apartment or your house into a moving van. It's basically a big game of Tetris. And this is what the shipping companies had to deal with back in the day. It was complicated to load the ship up and to unload it and dealing with all these different things. Now with the shipping container, it's equivalent to if you were playing Tetris with only one piece, that big, long, skinny one that you love so much. How easy would that be if you could play Tetris with just that one long one? I could play Tetris for days. That would be awesome. So now with these shipping containers, the shipping companies can easily take what they're shipping, put it in these little boxes, and then stack them all up like Legos. And it wasn't just the shipping containers, because by themselves they were great, but that wasn't the thing that made it great. It was the ecosystem around that. Once you created these standard containers, all of a sudden these cranes, these trucks, these trains were created to handle and transport all of these new shipping containers. So it took something that used to take days and weeks to unload a ship, and now you can do it in hours. So this by itself improved the global economy because it introduced a new way to ship stuff from China to the United States cheaper than what you could have done before. 90% of all cargo in the United States is now shipped using a standard container. And it's really impressive. So we looked at this and we said, great, this is a great idea. How can we take this information and how can we do it with applications? We basically figured that in order to do this, we need to do a few things. We needed to find a box that we can put around the application so that all the applications that are inside of it act the same way. They start the same, they stop the same, they run the same, you get the logs the same way. From the outside, you really don't care what's in there. You just know if I have to start this application, you run this command. Then, along with this box, we need to create an ecosystem so that we can easily move these things from one system to the next. So if you're developing on your development environment on your laptop and you want to move it to the test server, you shouldn't have to reinvent the wheel. You should just move it. You don't really care what's in the box. It should be the same thing whether it's an Nginx server or it's a Redis server. Just move that from one place to the other. If you do this, the matrix of hell becomes a lot more manageable because every piece looks the same. So the outside systems become a lot more simple. You don't have to worry about anything. So now that we have this goal of what we want the future of applications to look like, we sat down and we said, OK, what do we need to do in order to get there? What we did is we created six easy steps. And step one is we needed to create the actual container that housed the application. And back in my Java development days, what we ended up doing is when you had an application, you would deploy it to one physical server. After a while, we ended up running out of servers, and we didn't have budget to buy more servers. So what we ended up doing is we looked at the server utilization, and we noticed that the resources were pretty low on most of these servers. So we weren't getting the most bang for our buck out of these servers. So what we ended up doing is taking and virtualizing each of those physical servers and consolidating them onto smaller physical servers. This works great for monolithic applications, but it doesn't work great when you have multiple distributed applications like we have today. There's a great blog post that was written by a company called Scout, who do server and application monitoring, of a developer who's trying to set up his production environment on his laptop. And he goes into saying how the production environment has 16 different services that he needs to run. His first crack at it was to create a virtual machine for each one of the services and load it up on his laptop. After a quick test, he realized that he would need twice as much memory that his laptop would need in order to run all of his applications. So it wasn't going to work. So what we need is something a little more smaller than a virtual machine, but has the same capabilities. Enter the container. A container is an isolated piece of code, or basically it's an isolated area, bubble, so to speak, that you can put your code in that's just like a virtual machine, but you don't have to have the guest operating system. It ends up sharing the guest operating system and the kernel with the host that it's on. So if you're looking at it from the outside, from the outside of the container, it looks like a regular process, because that's all it really is. It's just a process with a little special bubble around it. But if you're inside the container and you look out, it's like a one-way mirror. You can't see anything on the outside. You think you're all by yourself on this great island. This whole server is all yours. You can do whatever you want. And you can set up resource constraints on these containers so you can have, set them so that they have maximum memory. You can set them so they have maximum CPU and all this fun stuff. And there's a lot of other tweaks you can make. So this allows us to create this container where we can stick our application, but it's not as heavy as the virtual machine. And you might be wondering, are they fast? So IBM did a couple tests, and you can see the slides here, where they compared Docker containers to virtual machines. And if you can't see the slides, basically Docker wins in every case as far as speed. They start up faster, they use a little less memory, they restart faster, all kinds of fun stuff. The slides will be available if you want to check them out later. So we got step one done. Next step is, now that we have these containers, we need to make them standardized and portable. So container technology wasn't invented by Docker. It's been around for a while. The problem with the current technology was it was a little hard to use. There wasn't that much documentation, and the support tools around it were a little limiting. So the only people that could really use it were the ones that could dedicate the resources to figure out how it works. So the big companies like the Facebooks and the Googles of the world. And these containers weren't portable. You couldn't move them from one place to the other. So what we want to do at Docker is take that same technology that the big boys are using and bring it down so that everyone can use the same thing. And the containers that we want to build are basically, they're portable, they're easier to use. We get a bunch of documentation, a bunch of tools to make you use them easier, and have the ability to move your Linux container from your Docker container from one server to another without having to worry about anything. The third part is we need to make containers super lightweight. One of the things about virtual machines is they require physical resources to be dedicated to the virtual machine. So if you want a virtual machine with 1 gig of RAM, 10 gigs of disk, you need to allocate that space to the machine, and you can't give it up to another virtual machine if it's not using it. So if you had 3 of them on the machine, you would have 3 gigs used, 30 gigs of hard drive space. And if one machine, or one virtual machine, was set up so it's using only 25% of the resources, it wouldn't be able to share that with the other virtual machines. So this is a great feature of virtual machines where you can guarantee resources to a machine, but you can't share them very well. So you're underutilizing your servers. With containers, you can do something a little different. Because you don't have to allocate the actual RAM to them, you just set a limit. If one process isn't using all its RAM, the other containers can use it. So the nice thing about this is it lets you better utilize your servers so that you can have better capacity and better density. One of the ways we do that is we use a copy-on-write union file system. You might be wondering, what does that mean? Basically, a union file system is just a layered file system. And when it comes to disk space, if you had a container that was 500 megs, you could easily, well, let me start over. I'll make it a little easier for you. So the way containers are built is generally you have a base layer. That base layer is usually your operating system, your CentOS, your Debian, your Ubuntu. And on top of that is what you add your custom code to. That base layer is reused amongst all of your containers. So the nice thing about that is if you had a 500 meg base image, but you wanted to run 10 of them, it wouldn't be 500 times 10 because that same disk space is shared amongst all those containers. And you don't have to do that. It's only 500 plus whatever the size of all your containers are. So if each one of your containers is only 10 megs, then that's 10 times the number of containers plus the base image. And so you're using a lot less space. And because of this, when you need to ship containers back and forth, you don't need to ship that base image with you. You just need to ship the difference. So it's a lot less of a payload to push and pull between servers. So it's a lot smaller of data. So instead of transporting gigabytes over, you're transporting megabytes. Now, the more important thing when it comes to this is we need to have a big ecosystem. Because if you just have this and only people that are using it are Docker, then how useful is that? You need to have server companies like Rackspace and all the other companies to provide support for this as well, or else you're stuck building this on your own machine and it's not truly portable. If the container companies would have, back on the cargo days, would have basically patented their technology and not shared it with the world, they would have had 1 or 2 shipping companies that would have this, and the rest of the people would do it the other way, and it wouldn't have spread to what it is today. So our goal is to basically build an open platform for anyone to be able to share and build and run and distribute their applications so that we can see what we have today. That platform is what you see here. The green is the engine, it's all the open source part of this. That and the APIs are all open. On top of that, we have a hub. It uses the same APIs. It allows us to build orchestration, monitoring, collaboration, image sharing with other people so that you can easily share your images and work more efficiently. This open platform has contributed to, these stats are a little out of date, but I think there's over 20,000 applications now that you can easily download. So you don't have to worry about going and running and building your own Redis server. You can just, someone already built one, you can go down and download it. You want to have your own Apache server, you can just go ahead and download it. It just saves you all that time. I believe there's over 13,000 projects now on GitHub that list Docker in the name. You can move between all these different providers and use any of these operating systems. So you have the flexibility to do all of this because there's an open platform. This open platform allows you to build, ship, and run. I don't know about you, but as a developer, one of the hardest things for me to do is I work on a project for a while, and I have to hand it over to QA. Because once you give it to QA, there's that, it's like your firstborn. You're giving it to them, and it's like the first day of school, and you're happy, but you're sad at the same time. Because you just know it's just a matter of time before they call you over and say, hey, there's a bug. And the first step of being a developer is denial. It wasn't me. It wasn't me. And you pass the buck. You say, oh, you must have tested it wrong. It must be the system administrators. And there's a lot of finger pointing. And in the past, this was the case because there was no way to guarantee that the server application that you had running on your laptop is the same as the test environment. So there was a lot of time wasted trying to figure out what's going on. With Docker, we allow the ability to run the same piece of code on your laptop as well as your test environment, staging, production. There's guaranteed that it's the same without having to worry about anything. So if there's something wrong inside of the container, you know for a fact that it's actually your code. If it's outside the container, it's an ops issue. eBay actually uses this to automate their process to make going to production a little smoother. So let me explain how you could use this. So inside of your source control repository, you can drop a Docker file. A Docker file is just this little file that explains to Docker how to build a container to run the application. So if you put this Docker file inside of your source code repository and set up an automated build whenever you commit, that means when you say, I'm going to commit some code, the automated build would trigger a little system that would say, download all of my code, build this Docker file given the instructions that I was given. If it runs successfully, upload it to the registry. You could then trigger your test system to say, pull down that latest image, run all of your unit tests. If those unit tests pass it off and run your integration tests. If all of those tests pass and you feel really confident in your unit and your integration test, you can push that right to production. So a process that used to take days, maybe weeks, can now be automated, and you can do this many, many times a day. All because of the fact that you know that the code that you're running now is going to be the same code that you're running later on. And that doesn't have to be with just a simple application. You can do this with distributed applications as well. The Scout manager, or the Scout person that wrote the blog post that I mentioned, ended up using containers to build their whole environment. So with Docker, he was able to do what he couldn't do with virtual machines. And he had the 16 different services all running together, and they were starting up super fast. So now when your developer comes in for the first day, all they have to do is get Docker running on their machine, give them a couple of source code repositories, and then have them run some commands, and boom, they have the environment. They don't have to worry about configuring the Nginx server or the database server or the Redis server. They just take what they have in production, the images that are already available, and they know everyone in the team is using the same images without having to worry about configuring, or some guy has one setting that's different than someone else's, which results in different code. The thing that's really important about Docker is it's the community and the ecosystem around it. Once again, these stats are a little out of date, and that's a good thing about this is every time we update these slides, they're out of date a week later. So there's now, I think, 600 contributors to Docker, and we only have 40 engineers in the company. So a majority of those people are companies like Rackspace and Red Hat that are contributing back to the community to make Docker what it is today. There's over 250 meetups in the world. 250, that's a lot. You got from Portland, Maine to Portland, Oregon. They've got one in every continent. The marketing team actually have this map in their office that you scratch off an area whenever they get a meetup. So they've got one in every continent except for Antarctica. So if anyone knows anyone in Antarctica, let the marketing team know, because they really want to scratch that one off. It says 6 million downloads. I believe we're over 20 million downloads. And 10,000 GitHub projects. I believe it's 13,000 at this point. So along with this community who have built these reusable images, as well as the partners that help provide the code and making it run on all their platforms, we also have enterprise support, better documentation, training, network of partners that will help do all of this stuff for us and help build the community, because it's not just us, it's the community that we're trying to build. Eventually, if the Docker company went away, the Docker community could keep going on and let the code live on its own. Here's a kind of a bigger slide that spells out all the different service providers that are out there, just so you can see all the different parts. And if you don't believe me, just ask anyone that's using Docker. We've got a bunch of them here. We had a conference a few months ago, DockerCon. If you go to the website, dockercon.com, there's a bunch of videos posted from all these different use cases that'll help you better understand how people are using this and how you can use what you need to do. The last step of the whole process is basically we need to build systems and infrastructure that take advantage of the new paradigm. If we didn't have the infrastructure in place, then it's not very useful, because if I can't move my container from one service to another, so I can start off on my development environment, in my basement. If that works well and I got some traction, I can move that to a cloud server on Rackspace. If all of a sudden I'm on Hacker News and I can't handle it, I can move that onto an on-metal server or a physical server at Rackspace, and then we can handle the load. And we let Rackspace deal with a lot of the stuff that we have to worry about. And because it's all running in Docker, then they don't have to worry about, oh, what is your application? How do you start it up? How do you do this? It's all built in. So in conclusion, there's multiple forces driving a way to set up your applications. We believe the right approach is to actually separate the application from the infrastructure. And we think that the container approach versus a VM approach is the right level of abstraction. You get to move around megabytes worth of stuff instead of gigabytes. And they're a little more flexible, and you can use more resources, and you get all the cost savings. This allows your infrastructure to be managed consistently and stably. It also helps you save money. The big thing about Docker is you want to save resources, save time, and at the end of the day, you want to be able to deliver your products the way that you do today without having the overhead of dealing with all of this matrix of hell. So we want to thank Rackspace for having us today. And if you need more, we have a couple of websites and places you can get the information. So.
Hey, everybody, give it one more. Thanks to Ken Cochran. Ken, thank you for coming and talking to us about Docker. We're big believers in Docker. We're big users of Docker. We love Docker. And thank you for coming and enlightening us on container technology. Thank you very much.